Hi, Innovation Day. I'm Phoebe.
I'm Holden.
I'm Tanisha.
And our senior design group has been working on a precision time-of-flight monitoring system for continuous prevention of endotracheal tube dislodgement in neonatal care.
To provide some context, endotracheal tubes are life-saving for neonates as they help the newborns breathe when they require mechanical ventilation. But the tubes also come with risks such as unplanned displacement, which can lead to serious complications like incorrect misplacement into the esophagus, which can be fatal. What makes this problem more concerning is the limitation of current prevention methods. Frequent X-rays can expose the infants to repeated radiation. On the other hand, sedation reduces movement but can interfere with crucial developmental processes. Additionally, most existing devices focus only on stabilizing the tube without providing real-time feedback. This lack of active monitoring means that displacements may not be detected immediately, and because of these limitations, the issue demands more attention. There is a clear need for safer, more effective solutions that can actively assist the medical staff in detecting and preventing complications in real time.
Our system will be able to detect within plus or minus 1 millimeter of endotracheal tube displacement, provide real-time feedback and alerts. Our device will reduce complications and improve neonatal safety in NICUs. So this is our prototype. Our adapter is on the left, seen attached to the ETT. In the middle is with the neonate bar, and on the right is the actual device itself. Our sensor is going to be sandwiched in between two parts.
Our methodology follows a rigorous path for the development of our project. Using the Arduino IDE, we developed a displacement tracking algorithm. It allows to capture a real-time baseline and triggers an alert when the sensor-defined threshold is breached. We used a time-of-flight sensor for high-accuracy distance monitoring, which is supported by a 2-inch LCD screen for real-time data visualization and a buzzer for immediate physical feedback. To move from a breadboard to a finished product, we created a custom housing in SolidWorks and 3D printed the final assembly in ABS.
All right, for computational testing, we performed a study in SolidWorks simulation to show that the weight of the device has negligible effect on the endotracheal tube. For specifications, we did an external force of gravity and also a 2-gram load to simulate the components inside the sensor and the wires, and one end was fixed to the ventilator side. On the left, figure A is our mesh and figure B is our final result.
Following this, we did some testing on the sensor itself, and we plotted the time-of-flight reading against the ruler as a golden standard, and this showed us great linearity and predictability. Next, we did residual plot analysis, which showed good reliability of our calibration. Following this, we did precision testing and found that the sensor has great precision, and we also plotted the percent error versus distance and found that the greater the distance, the improved accuracy. Overall, the average was 7.75% error. We also did some structural integrity and functional testing. The drop test passed. Alarm sensitivity was 1 plus or minus 0.05 seconds and plus or minus 1 sensitivity. There was 0 false alarms recorded, and the p-value came out to greater than 0.05 for a comparison between dark and light conditions, showing no significant difference in functionality between lighting conditions. Also, it's important to note here on the left is the SolidWorks drawing of the adapter, and here's the current user interface.
For ensuring the effectiveness of our device, we had a set of specifications and constraints. Our primary objective is a high proximity movement detection. Our system is created to detect a displacement within plus or minus millimeter within 3 seconds. And we also used a simple user interface that requires less than 3 taps to capture baseline, increase or decrease the threshold, or mute the alarms, which is important in an ICU environment. On the constraint side, we have emphasized a high alert specificity so that we can minimize the alarm fatigue while also limiting the leakage current to under 50 microamperes so that it meets the neonatal electrical safety standards.
So our results have demonstrated a safe and reliable method for real-time feedback. In the future iterations, we hope to add multiple time-of-flight sensors for improved monitoring. And then combining the sensor with other sensors such as capnography sensors would improve the reliability as well. Unfortunately, time time and cost constraints prohibit us and also fabricating an invasive device which would give better results. We will also continue to do more testing with the user interface to design something more in line with clinical needs.
And we'd like to acknowledge Dr. Lipping Tang and Dr. Eric Ortigoza for their guidance and mentorship. Thank you so much for listening.